Well, welcome back. This is section 9.1 and your new workbook 7B. So we're going to talk about number patterns and sequences. So let's say we have one dot, then the next pattern it goes to 3 dots, and then 5 dots, and then 7 dots. Let's try to figure out how we might predict how this pattern or sequence is going to grow. So we know when it's the first of the sequence, we have 1 dot. When we have the second of the sequence, we have 3 dots. And the third, we have 5. And the fourth, we have 7 dots. Now, if we look at this, we can see that each time, look at this, we're adding 2 dots to each one. All right, so we could predict how many figure 5 would have. So if we add 2 dots to 7, we'd have 9, and 2 dots to the next figure, we'd have an 11. And strangely enough, we could figure out how many dots a figure that doesn't even exist has. Figure 0. So if we subtract 2 from that, we'd find that we had -1 dots. And now that might seem kind of strange why we might want to find out what figure 0 had, but it's a very important thing to answer a few questions. So let's look at those questions. So in order to determine patterns and a rule for these patterns, we need to figure out how is it changing and how does it start. Using a rule to predict, we want to use a rule to predict figure 100 once we answer these two questions. So how is it changing? Well, we notice that it's adding 2. So plus 2. How does it start? Well, that's figure 0. Or when n equals 0. So it starts at -1. Now that's very important. So when we do that, we can predict a rule to find figure 100. So our rule is going to look like this. So the nth term, that's how we would say t to the n, the nth term for a linear pattern, that's very important, would be m times n plus b. So m is how it's changing. B is how it starts. So you may have seen this formula y equals mx plus b before, which is the slope-intercept form of a linear equation. So I'm just modeling that with a few different variables, tn and n. So tn is the same as y, n is the same as x. So let's look at what possible rule we might be able to use to predict that. So if we fill this in, we have Tn equals, and we saw how it's changing by 2. And then we can put an n in here, and it started at -1. So to simplify this, we can write Tn minus 1. Now, if we want to predict figure 100, we would just write t to the 100 equals 2 times 100 minus 1. So t to the 100th equals 200 minus 1, which is 199. Now, this little number right here is called a subscript. It is not involved with the math at all. It is only a name. So it means term 100, okay? Do not use this 100 for any math, okay? It is only a subscript and part of a name. All right, so now let's look at another example. All right, example 1. So if we have an input here, I'm going to put this is my first term, so I'm putting it under the 1. My second term goes under the 2. My third term goes under the 3 for n. My fourth term under the term for 4. Now, if I want to predict figure 5 and figure 100, I need to know what figure 0 is. So first of all, I need to see how it's changing. So when I look at this, I am adding 3. Okay, so that means that I know what figure 5 would be if I added 3 to this. So it must be 11 plus 3 is 14. Now doing that all the times that I need to get to figure 100 would be very tedious. So it'd be very helpful to have a rule. So to do that, I need to figure out what 2 minus 3 would be to get this term. So 2 minus 3 is -1 again. Now, it's not always going to be -1. It just happens to be my first 2 examples came out to be -1. So if I added 3 to -1, I would get 2. So that checks. So we would have a plus 3. So now if we used our general term, Tn, and we have how it's changing times n plus how it starts, we can fill in our equation. So Tn equals 3n, and then this is plus -1. So this is going to be 3n minus 1. Now to find T100, the 100 term, I can say 3 times 100 minus 1. So that's 300 minus 1 equals 299. So now I know it's going to be 299. All right, any questions? I wish I could answer. All right, let's go to the next example. Seriously, any questions you have, you can post them on my Google Classroom. All right, example 2. So our first term is 30, so it goes under 1. Our second term is 25, so it goes under 2. Our third term is 20, so it goes under 3. And our fourth term is 15, so it goes under 4. So when we look at how is it changing, ooh, it's decreasing by 5. So how would I go from 15 to the next term? Well, I just subtract 5. So 15 minus 5 is 10. Now, I would have to add 5 to this so that I could figure out figure 0. So that would have to be 35. And then that would fit the rule that I'm subtracting 5. And again, trying to figure out figure 100 would be quite difficult without a rule. So let's find a rule. And this is a linear pattern because it has a constant change like this, where I'm just adding or subtracting something. So I have Tn equals, and I have n plus something. This is how it changes. It's changing by -5. This is how it starts. It starts at 35. So my rule then is Tn equals negative 5n plus 35. So if I want to find figure 100, I just put the 100th term equals negative 5 times 100 plus 35. So that gives me negative 500 plus 35. So we have different signs, so we're going to take the difference. And the easiest way to do that is to subtract like this. And remember, since the biggest number is negative, our answer is going to be negative. So we'll carry 1 from over here and make that a 9, and this a 10. So we have a 5 and a 6 and a 4. So the 100th term is going to be negative 465. All right. So any questions you might have, please post them on my Google Classroom. Right, let's look at the next example. Oh, I forgot something important. Let's put that answer right here so we get all our credit. There we go. Okay, example 3. So this one is not a linear pattern. When we look at this, it changes by 2. So let's see, we have a plus 2, and then it's plus 6. So we can tell from the first 2 that this is not linear. So we can't use that formula that we were using, Tn equals m times n plus b. So we have to figure out something else. Now, one of the tricks you can do if it's not linear is just look at it and, 1 times what is 3? 3 times what is 9? 9 times what is 27? So if we can do the next term over the previous term, 3 over 1, and that equals 9 over 3, and that equals 27 over 9, which it all happens to equal 3 over 1, which is just 3, then we have a geometric sequence. So we can figure out that if we multiply 27 by 3, we would get 81. And if we divide 1 by 3, we would get 1/3. Now, this particular, to find this rule would be quite difficult. I can show it to you another time. It's more of an 8th grade standard, but you'd have something that looks like this: y equals ab to the n minus 1 when you were dealing with sequences. Okay, so in this case, b would be 3. So we have a 3 n minus 1. And a is the first term, which happens to be 1. So we have just 3n minus 1. So we can check this when it's 0. That'd be 3 to the negative 1, which is 1/3. 1 minus 1 is 0. So 3 to the 0 would be 1. 2 minus 1 is 1. So 3 to the first is 3. Okay, so this is n1, and this is, it's called the geometric ratio. Okay, so this is a geometric ratio. Normally it's written as an R, okay, or B. We used a B, but you'll see an R in many cases for that. All right. But that's not a 7th grade standard, just teaching you a little more. Okay, so let's look at this. We have 625 is our first term, 250 is our second term, 100 is the next term, negative 40 is the next term. We have the signs changing. Can you believe it? So we need to figure out something because that's pretty crazy. So what do you think possibly could be multiplying by these numbers to make it change every time? Well, if we think about it, a positive times a negative is that would be correct, a negative. And a positive times a positive is what? That's right, a positive. And a negative times a negative is what? A positive. Okay, so let's go look at this. So if we try to establish a geometric ratio, 250 over 625, that should equal the same thing as 100 over negative 250, which should equal the same thing as negative 40 over 100. Now, if we start reducing this, we can reduce this by, divide both of these by 125, and we end up getting negative 2/5. And if we divide this one by 50, we get negative 2/5. And if we divide this one by, how about, let's think about that. It's going to be by 20. So we have negative 2/5. So it checks. So our geometric ratio, which I was using B, but many times you'll see it as R, is going to be negative 2/5. So we can figure out what this one would be by multiplying negative 40 times negative 2/5. So let's put a 1 under there. So we have negative 40 times negative 2 divided by 5, which gives us a positive 80 over 5, which equals 16. So we can write a positive 16 there. Now, if we do this one more time and we have 16 times negative 2/5, we'll put a 1 under that. So we have 16 times negative 2 over 5 equals negative 32 over 5, which ends up negative 6 and 2/5. Now to find this one, we would have to actually do the reciprocal. Do you remember what a reciprocal is? Well, let's take a look at that one. Okay, so now if you remember, to get this, we would have had some number, so we'll say t to the n times negative 2/5 equals 625. So in order to get rid of this, it's multiplying here, so we'd want to multiply by the reciprocal on both sides. So let's do that. So remember, if we do it on one side, we have to do it on the other side. So we're going to do a reciprocal here and here. All right. Okay, so what happens there is these cancel, the 5s cancel, and the 2s cancel. I have 2 negatives, so now I just have t to the 0. And then I have to multiply 625 times 5, which gives me 25. Carry a 2 over here. Then 5 times 10, 2 is 10, plus 2 is 12. Carry a 1. 5 times 6 is 30, plus 1 is 31/2, and we have a negative sign. So this is going to end up being, when we divide it, we have 1, 2, and 3, carry a 1. 5 2s and 11, carry a 1. 6 2s and 12, and 2 2s and 5, and there's 1 left over. So we would have a negative 1562.5 for T0. Okay, so we can fill in that chart. That was a little rough, don't you think? Okay, so that's sometimes, it's not so easy to find figure 0. So we have negative 1562.5. All right, let's look at another example. Oh, here we go. So we're going to see how things grow. This will be kind of fun. So we have these, consider these like little matchsticks, okay? So with the figure 1, we're going to count. We have 1, 2, 3, 4, 5. So we have 5 sides on figure 1. Now we need to look at how many little matchsticks made this figure. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then for the third figure, we count the matchsticks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have 13. So we look at how is it changing. This adds 4, and it changes, and it adds 4, and there we go. We have a constant change, so we can tell what figure 4 would have. So figure 4, we add 4 to 13, and we'd have 17 matchsticks to build this pattern. And then if we want to find figure 0, we subtract the 4. So that gives us 1. So 1 plus 4 equals 5. So when we fill out how is it changing plus how did it start, it changes by 4. So we put the 4 here. It started by 1. And this works for linear patterns. So if we want to figure out T100, again, all we have to do is 4 times 100 plus 1 equals 400 plus 1 equals 401. And there you have it. Okay, that concludes section 9.1. I will add 9.2 very shortly. Have a wonderful day and be well.